Hey everybody, this is 3.0, the gravitational force. So it says, Angela, Blake, and Carlos are studying the data table to the right, which shows the mass, orbital radius, and orbital period of 4 planets. They note that the orbital period increases, but disagree about why this happens. Their arguments are as follows. So I've put them right here. So here's the data table. You can see here we got Mercury, Venus, Earth, and Neptune. It shows that their mass keeps going up. It shows that their orbital radius keeps going up, and it shows that their orbital period, that's how many years it takes to go around the sun once, keeps going up there as well. So Angela says it appears that the more mass a planet has, the longer the period is. This is because more massive objects are more difficult to move, so these objects move slower in their orbits. Blake says, no, all the planets move at the same speed around the sun, but planets with greater orbital radius must make longer circumference orbits, causing their orbital periods to be greater. And Carlos says it is the case that the farther radius planets must make farther circumference orbits, but the farther the planets also go slower, the farther planets, also go slower because there is less gravitational force acting on them. So who is correct here, or are they all partially correct? So for this problem, consider one of the planets of mass m, lowercase m, making a circular orbit of radius capital R around the sun of mass capital M. Let v represent the speed of the planet as it orbits the sun, and t, capital T, be the orbital period there. So part A, beginning with basic equations from gravitational and centripetal force, and equation that and centripetal force. And an equation that relates speed and period of circular motion, derive an expression for the orbital period of this planet in terms of r, m, v, and physical constants as necessary. Note that it may be helpful for part B for you to number your steps so that they can be referenced later. All right, so let's start with step 1. So this thing, the force of gravity on them is a centripetal force. So I'll say the sum of the forces is mass times centripetal acceleration, just like we begin all of these. So step 2 then, I will sub in for these. So the force that's acting on them is the force of gravity, and that gives us mv squared over r, where lowercase m is the thing going in a circle. Step 3, let's substitute in. This is Newton's universal law of gravity. So it's the universal gravitational constant times one mass, which is the sun, big M, times the other mass, which is the planet, little m, over r. And I'm going to actually write these r's as capital. And that is equal to mv squared over r. So step 4 now, we get to cancel some things out and rewrite. As you can see here, the little mass is on each side of the equation. The radius here cancels with one of the radii there, so let's simplify this. Gravitational constant times the mass of the sun divided by the radius is equal to v squared. So a little side note I'll put in here in this case, remember that velocity of something that goes in a circle is equal to the circumference, 2 pi r, divided by the period t. So let's use that then to do the next part. This velocity we'll put in here and we'll square it. So gravitational constant times the mass of the sun divided by the radius is equal to, everything here gets squared, so 4 pi squared r squared over t squared. We get a little bit of rearranging to do here then next. So whoops, let's also number this. This is step 5 right here. So step 6, I'm just going to multiply everything around. I'll bring the t squared up to this side. I get 4 pi squared r cubed when I bring that r up, divided by g m. And so the last step is really basic, but I'll go ahead and call it one more step there. So the period is equal to the, and I can even bring these two things out. I'll bring out the 2, I'll bring out the pi. I'll leave the r in there, otherwise it gets confusing to have r in 2 spots. So there, a little bit simplified there. So 2 pi times the square root of r cubed over universal gravitational constant times the mass. So let's use this to talk about their different arguments and who's right and who's wrong. So Angela, if you remember, let's look at hers. She says the more mass a planet has, the longer its period is. So she says the more mass causes the longer period. But let's look at our equation here. So the mass of the planet cancels out. So we want to say that with Angela, actually here for a moment. Angela is incorrect. And the reason for that is the mass of the planet cancels out. Let's look at Blake's argument and put it to the equation here. So Blake says, no, all the planets move at the same speed. I don't know where he's getting that. So, around the sun, but the planets with greater orbital radius make longer circumference orbits, causing their orbital speeds, their orbital periods to be greater. But if we look here, the only thing, 2 is a constant, pi is a constant, g is a constant, the mass of the sun is a constant for all the planets. So the only thing that matters is the radius. So he is right, the bigger radius, the bigger the circle to have to go through, but there's no reason to assume they all have the same speed, and therefore it affects the radius and the period there. So finally, let's look at Carlos. Carlos says, it is the case that farther radius planets make farther circumference orbits, but the farther planets also go slower because there is less gravitational force acting on them. So that is true, because over here we see that the gravitational force, which causes the centripetal force, has to do with the distance from the sun squared. So if you double your distance from the sun, then you have 4 times less force acting on you. So Carlos is actually right there. And in the end, it just works out that the period is solely dependent upon the radius, in other words, the distance you are from the sun.